In this lesson, we'll do a quick review of power series. So first of all, what is a power series? Well, a power series is a series of the form. So sum, and it could begin at any number, but we'll just say r starts at 0 and goes to infinity. Has some coefficients a(n), and then it's x minus some other constant number c to the nth power. So you have power x raised to various powers of n. It's kind of like a polynomial sort of ish, except for it has an infinite number of terms. And you can think about this as a function f of x, whose domain is the set of all x such that the series converges. And that set of all x such that the series converges, that is called the interval of convergence. Now, next, what is the radius of convergence of a power series and how do you find it? So the radius of convergence is a number r such that the power series converges if the absolute value of x minus c is less than that r, and diverges if the absolute value of x minus c is greater than r. When that x minus c equals r itself, the series may converge or may diverge. And in terms of how do you find it, you apply the ratio or root test, depending on what's sort of more appropriate, to your power series. And when you do all the work, you have ... all sorts of stuff. You end up with something has to be less than 1. And you figure out when is this expression, this x minus c, some expression of stuff less than 1. And that is how you find the radius of convergence. Now, what is the interval of convergence of a power series? This is the set of all x such that the series converges. And you kind of piggyback on the last slide. You find the radius of convergence. So you're going to end up with some absolute value of x minus c is less than an r. Translate that into negative r less than x minus c, which is less than r. Negative r plus c will be less than x will be less than r plus c. And then you test these in your power series. And the reason that you have to test those endpoints is that at those values of x, when you apply the ratio or root test, you get the result of 1, which is inconclusive and it could go either way. So you have to actually test those endpoints, and it will use some other test other than the ratio or root test. All right, let's do a few. So find the radius and interval of convergence of the following power series. So here the root test is not really a good option because of that n factorial, but the ratio test will work just fine. So let's find the limit as n goes to infinity, absolute value of a(n) plus 1 over a(n). Now when you input n plus 1, we have x minus 2 to the n plus 1 all over n plus 1 factorial divided by a(n), or multiplied by its reciprocal. So multiplied by n factorial over x minus 2 to the n. Okay, that simplifies into x minus 2 to the n times another x minus 2 n factorial over, now n plus 1 factorial, that's n plus 1 times n minus 1 all the way down, so n plus 1 times n factorial. And a whole bunch of stuff should cancel. The x minus 2's cancel, the n factorial's canceled, and since n is a positive integer, we can assume that n plus 1 is positive, so that can come out of the absolute value bars. But x may be a negative number, so x minus 2 has to stay in. All right, now, as n goes to infinity, remember that that x minus 2 is a constant. So you have a constant divided by something that's getting bigger and bigger and bigger. This will go to 0. Now this is the stage when students erroneously conclude that the radius of convergence is 0. You have to stop and think about what the ratio test tells you. If the result of the ratio test is a number that's less than 1, your series converges. The result of this limit is 0 all the time. 0 is less than 1 always, no matter what x is. And as that is the case, that means that this series will converge for all x. So this series converges for all x. In other words, your radius of convergence is infinity, and your interval of convergence is minus infinity to infinity, or the entire real number line. So a ratio test result of 0 means that the series will converge no matter what x is. Now on the flip side, here's one that's going to be similar but be the other conclusion where you only have convergence at one point. So once again, let's apply the ratio test. Okay, so when we input n plus 1, we have n plus 1 factorial 2x minus 1 to the n plus 1. All that over, so that's a n plus 1 over a n, which is n factorial 2x minus 1 to the n. And the same simplification applies. We end up with the absolute value of n plus 1 times 2x minus 1. And the n plus 1 can factor out of the absolute value because it's positive. Okay, now as n goes to infinity, we are going to have something infinite times some finite number. So this is going to be infinity. And infinity is bigger than 1, like really, always. Unless one thing, unless that 2x minus 1 equaled 0. Or in other words, unless x was equal to 1/2. If x was 1/2, we'd have some number times a bunch of zeros. So the limit would be 0, which is less than 1. So this thing converges when x equals 1/2 only, nowhere else. That means the radius of convergence is 0, and the interval of convergence is the number 1/2. All right, let's do a few examples where you have to actually test the endpoints. So find the radius interval convergence of this series. So once again, this n squared that's in the denominator there, that sort of screws up the ability to use the root test. So we're stuck using the ratio test. Oh, bummer. So find the limit as n goes to infinity of absolute value a n plus 1 over a n. Okay, so we'll input n plus 1. We have x plus 6 to the n plus 1 over n plus 1 quantity squared, 8 to the n plus 1, times n squared, 8 to the n over x plus 6 to the n. All right, now canceling some stuff here, we'll end up with an x plus 6 in the numerator, an n squared. Let's just color code this. So this x plus 6 and that x plus 6 will cancel some once just with an x plus 6 to the first. This 8 to the n and this 8 to the n plus 1 are going to cancel, leaving you an 8 in the denominator. And we'll have n squared in the numerator and n plus 1 squared in the denominator. And that can also be written as follows. It can be written as n over n plus 1, the quantity squared, times the absolute value of x plus 6 over 8. Remember, x could be a negative number. That's why you have to have, well, x plus 6 could be a negative number. That's why you have to have that x plus 6 in absolute value bars. Now, as n goes to infinity, this n over n plus 1, that will go to 1. 1 squared will be 1. So this limit is x plus 6 over 8. And we will have that this series converges by the ratio test if this result, this x plus 6 over 8, is less than 1. And that implies that x plus 6, absolute valued, is less than 8. And that 8 is your radius of convergence. Now we would like to find the interval of convergence. So take the fact that you know that x plus 6 absolute valued must be less than 8. That is the same thing as saying negative 8 is less than x plus 6, which is less than 8. Take away 6 and we have negative 14 is less than x, which is less than 2. So now we know that this series will converge if x is between negative 14 and 2. What we don't know is what happens at negative 14 and 2, because at those values of x, the result from the ratio test will be 1 and will be inconclusive. So the only way to know is to plug them into the series and see what comes out. So when you plug in negative 14, so we have a sum from n equals 1 to infinity, x plus 6. Negative 14 plus 6 will be negative 8 to the n over n squared times 8 to the n. Well, negative 8 to the n over 8 to the n, the 8's can cancel, just leaving you negative 1 to the n over n squared. And this series would converge. Tell me what test you would use. You would use the alternating series test. The limit of the terms, 1 over n squared. The 1 over n squared goes to 0, and 1 over n plus 1 squared is certainly less than 1 over n squared. But it's enough to just say you recognize that it would be the AST. Now at x equals 2, you have the sum from n equals 1 to infinity. Now 2 plus 6 will be 8 to the n over n squared, 8 to the n, which is the sum from n equals 1 to infinity, 1 over n squared. And this converges. It's a p-series with p equal to 2. So in this case, we have convergence at both of our endpoints, and our interval of convergence, which I'm going to abbreviate IOC, is negative 14 to 2, inclusive of both endpoints. All right, one more. Find the radius and interval of convergence of this series. So once again, ratio test. Take the limit as n goes to infinity. Absolute value of an plus 1 over an. So that's 2 to the n plus 1, x minus 3 to the n plus 1 over root. Well, we'll have n plus 1 plus 3, that's n plus 4 inside that root sign, times root n plus 3 over 2 to the n, x minus 3 to the n. And let's go through term by term and figure out what pieces are going to cancel. So with this 2 to the n plus 1, and that 2 to the n, the 2 to the n's will cancel, leaving us just 2. Same here with the x minus 3's. We'll have just times an x minus 3. And the numerator will have a root n plus 3. Denominator will have root n plus 4. So we have the limit as n goes to infinity, 2 times the root of n plus 3 over the root of n plus 4 times the absolute value of x minus 3. And that can be expressed as n plus 3 over n plus 4 times the absolute value of x minus 3. And as n goes to infinity, this n plus 3 over n plus 4 goes to 1. So this is twice the absolute value of x minus 3. And we will have convergence if this to absolute value of x minus 3 is less than 1, or the absolute value of x minus 3 is less than a half. So this tells us that our radius of convergence is 1/2. Now we just need to figure out what the endpoints are and test for convergence or divergence at those endpoints. So knowing that the absolute value of x minus 3 has to be less than a half, that implies that negative 1/2 is less than x minus 3, which is less than a half. And adding 3, so 3 is the same thing as 6 halves, so plus 6 halves plus 6 halves. So 6 halves minus 1/2 is 5 halves. It's less than x, which is less than 7 halves. Okay, so let's plug those in and test them. At x equals 5 halves. That means we have the sum from n equals 1 to infinity, 2 to the n. When we plug in 5 halves for the x, we have 5 halves minus 3. That's negative 1/2 to the n over the root of n plus 3. And that simplifies further into the sum from n equals 1 to infinity, negative 1 to the n over root n plus 3. And this will converge by the alternating series test. At x equals 7 halves, we have the sum from n equals 1 to infinity, 2 to the n. Now 7 halves minus 3 will be positive 1/2 to the n, which is the sum from n equals 1 to infinity of 1 over root n plus 3. That looks awfully like 1 over root n, which would diverge because of a p-series. So this will diverge. My suspicion is that you cannot make the inequality go the right way to prove divergence with direct comparisons. You'd have to use the limit comparison test. And the interval of convergence includes 5 halves, but does not include 7 halves. You can express it like that, or you could say 5 halves is less than or equal to x, which is less than 7 halves. Both of those are totally fine.